Good morning to respected faculty and everyone. Myself K. Manoj Kumar Reddy from 4th year EED section in Annamachari Institute of Technology and Sciences, Rajampet. My teammates G. Manjula, K. Someshwar Reddy, R. Bhaskar. We made a project on enhancing power quality in integrated PV and DFIG systems through MPPT and Fuzzy logic control for grid systems under the esteemed guidance of Mr. M. Sai Sandip sir, Assistant Professor. Now let's delve into the project. Now let's introduce into the project. Firstly, there are many challenges in power quality enhancement and in renewable energy integration. In order to reduce these challenges, we implementing or employing the MPPT algorithms and fuzzy controller, where MPPT is used to optimize the PV system operation for maximum power output, and fuzzy logic control regulates or enhance the DFIG system's stability while integrating with the grid. But while integrating these may lead to power quality issues like voltage instability, harmonic distortion. In order to reduce this, we implement again incremental conductance and fuzzy logic control techniques. These are shown through simulation and experimentation models. Now, the main objectives. Main objectives of this system are solar photovoltaic and DFIG wind energy systems integration. Here, we implementing MPPT techniques for maximum power extraction, developing fuzzy controller for smooth grid integration and harmonic distortion minimization, optimizing energy conversion efficiency. We enhancing the grid stability by using advanced control techniques and environmental benefits for integration. Existing system PA controller. In the existing system, we uses rotor feedback mechanism. The PI controller that eliminates steady state offset by using output based an error. Here, in order to extract the maximum power from wind, we use rotor control feedback. But there are many limitations by using the PI controller, like swiftly adapt the dynamic shifts in wind condition due to stiffness and reliance upon rotor control feedback. This may lead to inadequate power extraction and power quality. Disadvantages of existing system: sensitivity to parameter changes, tuning challenges, difficulty in handling disturbances, voltage instability and harmonic distortions, risk of oscillations and overshoot. Now, this is a proposed system. In proposed system, we used fuzzy controller, MPPT techniques like incremental conductance method, fuzzy logic control method. Here, this is the integrated system of MPPT and DFIG with grid. In this block diagram, it shows that here MPPT low frequency controller. This is the wind turbine, gearbox, DFIG, RSC, rotor side converter, GSC, grid side converter, filters, transformer, grid. This is the control block. Mainly, low frequency control MPPT controller is used to change the rotor positions of the wind. Where DFIG means which allows the power from both stator and rotor. Here mainly stator supply is synchronized with the grid, so stator supply is directly given to the grid, but rotor side supply is not synchronized with grid, so mainly we use a rotor side converter from converting AC to DC, and here we use a DC link to minimize or reduce the distortions or to continue stabilize supply, and this supply is given to the grid side converter, which is again converted into DC to AC, where here we use filters to reduce the distortions, and it is given to the transformer, which changes the voltage levels, and it is given to the grid. Here H infinity controller. H infinity controller is an advanced control strategy which is used to achieve robust performance or stability of the system. This is the simulation block diagram of the system. This is the proposed simulation model of the system. Here, this is the here are three parts. One is DFIG, second one is grid, third one is solar. Here grid is 3-phase source, 3-phase VI measurement, distributed parameters, 3-phase breaker, 3-phase transformer. This is connected to RLC load. Here solar, mainly here the solar input are irradiance and temperature. This is the voltage source converter, LC filter, universal bridge, MOSFET. MOSFET used for fast switchings and reduce the losses, etc. This is the DFIG block. Already I explained the integration of. Already I explained this block, MPPT and DFIG integration with grid. Now this is the PVR and DFIG datasheet. Here there are number of parallel 6, series connected modules per 9, cells per module 50. Now MPPT control techniques. The maximum power point tracking. Why we use maximum power point tracking means in order to extract the maximum power from the PV array under the temperature and irradiance as the input. Mainly this is the method we used here, incremental conductance method. Here we use two sensors, voltage and current sensor. Algorithm works as a comparing of the ratio between derivative of conductance and instantaneous conductance. When this instantaneous conductance is equals, then the solar maximum power point is reached. Here 0 at MPP, the maximum power point is reached. When negative at right of MPP, the dp by dv is less than 0. Then it is negative at right of MPP. Where the positive of left of MPP, dp by dv is greater than 0. This is the incremental conductance algorithm. Mainly here the initialization, this is the start block is the initialization. di I k plus 1 minus k dv v k plus 1 minus v. Here the incremental conductance is calculated derivative of current concerning voltage. The incremental conductance is compared with reference conductance from the previous iteration. When when the dv change in voltage is reached 0, then if no e is similarly 0, then it is going to update. If yes, di equal to 0, then if yes, it is also going to update. When there is no di is less than 0, then it decreases the duty cycle or increases the duty cycle. This is the simulation model of incremental conductance method. Here the PV array's input is irradiance temperature, which is combined with series RLC branch MOSFET, series RLC branches with boost converter control. Here we use boost converter control in order to operational position to optimum power. The boost converter contains diodes, capacitors, switches and inductors. RLC branches and diodes indicates the electrical properties of both power transformer and load. To control and monitor the load, measure its voltage and current. This is the methodology of fuzzy controller. Rules: fuzzification, inference, defuzzification. Here we given inputs. Crisp inputs are given to fuzzifier. The fuzzified inputs, fuzzy sets, are given to inference engine. Where rules database, fuzzy rules are given to inference engine, which are fuzzy conclusions. Implied fuzzy sets are given to the defuzzifier, which is again get into crisp outputs. This is the fuzzy controller. Same as the incremental controller, we changed the fuzzy logic controller and PWM generate in order to get a fast response and reduce distortions and better maximum power extraction. This is the fuzzy rules table, fuzzy surface diagram. If voltage is low voltage, then current is low, then the duty cycle is low. If advantages of proposed system: enhanced energy harvesting, efficient power generation, improved grid compatibility, reduced dependence on grid, environmental benefits and adaptive control. These are the simulation results of PI controller and fuzzy controller. Now let me run the program. PI controller and fuzzy controller. Here mainly the spikes are high when it is compared with fuzzy controller. The harmonics are high. Whereas PI controllers are commonly used control systems to set a desired point, such as in PV system, to regulate the system's output power. But while compared to fuzzy, the PI controller has many disadvantages, which while it may impact on load voltages, uh, exhibits the rise with increasing frequency. This is the fuzzy output waveforms. These where voltage and current are in phase. These are the load total harmonic distortion of PI controller and PI controller for voltage and current. Whereas the load voltages affects while using the PI controller. The total harmonic distortion is high in voltage 3.47% and PI controller is 12.76%. While using the fuzzy controller, we reduced it to 0.5% to 3.39%. By comparing the both PI and fuzzy controller indicates the substantial benefits. The fuzzy controller has total harmonic distortion of 0.50% and more efficient output waveform. Furthermore, the fuzzy controller reaches the current limitation of 3.89 amps at 71%, resulting in the lower energy usage and impact on the system. Finally, I conclude that by using the fuzzy control systems, we can regulate or enhance the stability of the system. And by using renewable energy integration, we can reduce the dependency on the grid. Thank you.